All right, so welcome. I'm Hannes Fassard from UNM Research Digital Institute. So I'm a senior researcher there in the Smart Media Solution team, and we are researching. The focus of our research is on video analysis, so all kinds of stuff like video quality check, video and film restoration or enhancement, and also general semantic analysis of video, stuff like object detection, face recognition, and similarity matching, and all these semantic information. All right, so first, a brief overview about the whole Hyper360 toolset. So the main goal of the project is to develop a whole toolset for interactive 360 video with a number of advanced and next generation features. So one can add interactive elements, so hotspots, also 3D captured human performances, acting as mentor, hyperlinks, and to other audiovisual elements. Furthermore, the toolset provides a personalized experience via tracking of the user preferences, automatic camera path, and quality check, and more the like. So it's a 3-year project, and it's in its final phase. So it's ending this month, and there are a couple of partners from Italy, Germany, Hungary, then Greece and Austria. So there are a couple of research partners like UNM Research and Fraunhofer and CERT, and there are also user partners, Mediaset and RBB, and company partners like Drucker, and exploitation partner and dissemination partners is OLKS. Toolset can be segmented in 3 phases or 3 steps, tools for 3 phases. So the first phase is the capturing phase. Here we have developed the Omnicab tool for high quality 360 video capturing with a vast array of cameras. Then there is the Caption tool for recording 3D performances of humans, which can be later fused into the 360 video. Then in the post-production phase, we have the OmniConnect tool, a web-based tool for annotation and adding all these interactive elements of the 360 experience. And then in the delivery and play out phase, we have first of all the OmniCloud, which is the backbone cloud service for providing all these services. And then we have the OmniPlay, which is a tool, a set of players for a variety of platforms like PCs or smartphones and so on. So more information for each of these tools. So the OmniCab tool provides as a set of features like that it supports modern capturing rigs, so multi-camera areas, or also tiny fisheye lenses devices. And it enables simultaneous operation of these mixed camera architectures. It integrates also a set of algorithms for video quality check of the 360 video. I will describe that later in more detail. Yeah, and it exploits the power of modern workstations very well. So then the Caption tool. This is the tool for capturing the performance of a human actor in 3D. So it uses a couple of Kinect cameras, which are, I think, 3 or 4, which are located outside of the human actor, and it provides near real-time 3D capturing of these actor, which can act then as a mentor. Yeah, then the OmniConnect web-based tool for the post-production and for the annotation. So here one can add all kind of interactive elements to the 360 video. So that can be a 2D item, like a video or a website or some text. You can add hyperlinks to other 360 videos, or you can add also the recorded human performance, which can act then as a mentor, which can, for example, guide you through the 360 experience. And it provides also integration of the so-called recommendation engine, which, based on the personal preferences, can dynamically highlight some elements which might be more relevant for this person. So then the OmniCloud service, it's a cloud service and uses the Amazon Web Service for video streaming, so to provide a smooth playback because the OmniConnect has also a player integrated for preview. Then the OmniPlay players. So here we are supporting PCs via web, also mobile devices, Android and iOS. Also, we support HMDs and also smart TVs via HBB-TV. Yeah, so here in the player, we are collecting these user preferences for profiling, statistics, and recommendation. And we have here also a tool for automatic camera path generation, which can render a classical 2D video from a 360 video. And this 2D video could then be viewed on older TV, which don't have smart TV functionality and stuff like that. So the last thing is the recommendation engine, recommendation process, which uses the learned preferences and semantic profiling to provide this personalized highlighting of some elements. It uses a background knowledge, learned background knowledge about the specific domain of interest of this video. All right, so that's it for the introduction. So I first will describe the quality check a bit technically, and then I will give a live demo. So what is quality check for 360 video? So the quality check detects defects and impairments of captured 360 video. So that can be stuff like blurriness, noise, flicker, and other defects. Here at the right side, you can see visual examples for some of these defects. The first two from the left are block defects, block dropouts, stuff like that. And the image to the right shows noise impairment. The use case for this quality check for 360 video is for on-site quality control. So you can check on-site during capturing if everything went well with the capturing. And if that was not the case, for example, you have a too high noise level because lighting is not sufficient, or the camera gain is too high, then you can change the capturing situation. So change camera parameters, or change the lighting. For 360 video, it's good for some defects when you have also localized information. So in order to see which of the image regions really are affected by the defect. So in the Hyper360 capturing phase, the QC pass is done automatically after the capturing. So it is invoked via the OmniCab tool. And it checks for defects like blurriness or noise, flicker, signal clipping, blocking artifacts, major video artifacts, and luma range and freeze frames, and some more. And the defects can be visualized very nicely in a GUI in our QC summary. So some technical information about the extensions and adaptations we did for the QC algorithm. The QC algorithms for 360 videos, they are in fact based on an existing set of detectors for classical 2D video or film. And these existing detectors, these are available in our QC solution VideoCert. So that's a product which is mainly geared for film and video archives. You can see it on the right. The summary application. And the thing is that 360 video has some unique issues to it, which make it necessary to extend the existing algorithms. So these are issues like, first of all, the equirectangular projection. That means that's the usual projection for 360, for recorded 360 video. But it means also that the image content is heavily distorted towards the poles. So you can see that in the, especially in the upper and lower image border. So that's an issue. The other thing is, that's 360 image. It's capturing the whole scene, of course. And for some detectors like signal clipping or blurriness, more localized defect information would be better. And the third thing is that the high resolution, so 4K or nowadays in more 8K, these high resolution of 360 videos, that means that the QC algorithms have to process a lot of pixels, so there is a runtime issue. So how we handled that? For the equirectangular projection, yeah, we adapted several of the QC algorithms in order to account for that. The specific adaptations, they depend a bit on the workflow on the existing QC algorithm, because every QC algorithm has a different set of steps. But the general recipe is that we are calculating a distortion map, which is then taken into account in some proper form. For example, using it as a weight map by which one can multiply some the values. This distortion map can be seen on the right side on the upper. Then for the localization, we adapted several of the algorithms so that they provide this localized information instead of providing only one value for the whole image. And for that, the general recipe was to divide the image into a matrix of tiles, calculating a local defect magnitude for each tile, and fuse it. On the right side in the lower part, you can see some intermediate images for the blurriness algorithm. So the basic principle of this algorithm is to calculate first an edge image, which is the middle image, and then for all the edges, measuring the width of the edges. And in the very lower image, you can see the blocks which have been taken for calculating the blurriness map. Then for the runtime enhancements, so we optimized the runtime of several of these algorithms via a combination of different but classical strategies. So first of all, we parallelized parts of the algorithm on the CPU by employing multiple threads. You can do that very easily with OpenMP. Then we were, for the most computationally expensive components of the algorithms, we ported these to the GPU. We use here CUDA, so that works only for NVIDIA GPUs. And we are skipping regions near the poles because that's usually the floor and the ceiling, so there's not much interesting image information in there. So now I give you a lifetime of the QC summary application. So I have pre-processed here already some of the 360 videos. So this is the QC summary application, and as mentioned, it provides a very nice timeline view for each of the defects and measures, and you can see at a glance in very short time in which regions of the video defects are occurring. So here are the timelines for the individual defects. So here on the upper left, here is some summary of the detected, a list of the detected defects. And this is a zoom view. And here, of course, you can see that's the video player. So you see here, a concert video. Yeah, and what we can see now from the defect timelines, we can see there are no blocking or block dropouts or video breakup defects, also no freeze frames. We have issues with the signal clipping, so game mode and clipping throughout the whole video. That's very typical actually for 360 videos. So this was taken, I think, with Insta360 Pro, and you have the fisheye cameras in these lenses, in these 360 cameras, and the sensors. They have a limited 8-bit range usually, so and that leads to so they have a limited dynamic range, and that leads to issues with with undershoots and overshoots. So the signal clipping is present throughout the whole video. Then there is a bit of a noise, but not a lot. And then there is no blurriness present, so the video is sharp, has its original sharpness, and there is a mild form of flickering throughout the videos, which is understandable because it's you see all these lighting effects. And what we can see, what's interesting is that there is a major peak in flicker, and that's actually our flicker detector is not only detecting flicker, but also major brightness related defects. And this peak is actually so as you can see here, it's a defect. It's a problem with the lenses, I suppose, and we are detecting this very nicely. So this is this peak here in the flicker measure. Yeah, there is also some other useful information like the audio spectrum, but channel info. What I would like to show also is the localization. So for game mode and clipping, we can see here, activate the localized information. So here we have a mask which shows us in blue the regions which are too dark, and in red it shows us the overshoot regions. So the regions where the image is too bright. So that's the localized information, and you can even play that. All right, so that's it for the quality check summary. So the next would be the AI models, also attached to the OmniCab, and also to other models of the tool set. Object detection and tracking. The automatic detection and tracking of all the objects in the scene is, of course, a very valuable semantic information which you can extract from the 360 video. The objects one is usually interested is objects like persons, faces, animals, vehicles, so stuff like that. And that provides first of all, the possibility for semi-automatic annotation of objects in the capturing application, as well as in the OmniConnect annotation tool. So one could think of adding hotspots very easily to a moving person or moving object of another type. So that's the first use case, and the second one is it's also a crucial information for the automatic camera path generator. So the task of this object detector and tracker, which we call Yoko, is to detect and track all the objects appearing in the scene, and each scene object gets a unique ID, and it has its own path, so you know for each frame where it is in the image. It gets a rectangle around. So we are detecting the 80 MS Coco classes from the MS Coco dataset. These are classes like persons, certain animals, cars, bicycles, and so on. And we have also custom networks trained for faces, text, and logos. The principle of the algorithm is that it combines state-of-the-art algorithms. First of all, the YOLO for 3 algorithm for object detection. So that's a deep learning algorithm, of course. And it's a good compromise between runtime and quality. And it's one of the most used object detection algorithms right now. We combine that with a high quality optical flow method, which runs on the GPU. This method calculates the motion pixel-wise between 2 consecutive images. And we use here the so-called TVL1 algorithm. Our algorithm is real-time capable. Yeah, so a bit more on the technical side regarding the workflow. So when you have 2 consecutive images or frames of the video, you're first calculating the motion field between the current and the next image. Then you are invoking also the object detector for the next image, and you get the list of detections. Then we are predicting for all the scene objects we have in the current image, their location in the next image. So we are tracking them, and for that we are using the motion field, the calculated motion field. You can see the motion field visualized in the upper right slide part of this slide. Then we are matching the predicted scene objects against the objects which have been detected in the next image. And for that, we are using the so-called Hungarian algorithm. Yeah, and we are updating the object state. So for existing objects which we couldn't match, we are declaring these as lost and we delete them. Usually that is because they got occluded by another object. On the other side, unmatched objects which have been newly detected are objects which are appearing newly, and these are added to the list of the scene objects. So to this algorithm, we added later also a separate person re-identification component. The problem here is without this re-identification step, when you have persons which are getting included and they reappear late later again. And these persons would get a new ID, so they would be handled as a different person. And that's not good, for example, for annotation. For this person re-identification, we are using a deep learning-based algorithm based on similarity matching of features which are derived from the person's appearance, like from the clothings and so on. Yeah, that could be useful also for objects, other object classes, but actually usually persons are the most interesting object class, so it's most important to have that for persons. On the right side, you can see different appearances of a person throughout the video. Yeah, so these have to be matched based on their similarity. Okay, then I will show first a demo video, so a pre-calculated video with the result of the object detection and tracking, and then I will give a live demo with a video courtesy of the Salient 360 dataset. All right, so this is a media set sequence. You can see first the result of detection and tracking for the 80 MS COCO classes. This is a network trained only for face detection and tracking. So you can see also small faces are detected well. And this is a network with 500 object classes from the Open Images dataset. So you can see here that also we have object classes like trees or plants or buildings. Like here. Yeah, but on the other side, it's not that accurate like the network trained only for 80 object classes, because the more objects a network has to detect, usually its performance goes down. Okay, then I'm gonna show you a live demo. So here we are using 3 networks. We are loading first the network weights for the 80 MS COCO classes, and we have also a separate network for face detection and another network trained only for text detection. So you can see overall it works quite well. There are some errors like detecting this as a sink or this as a suitcase, and missing some of the curved text here. But in total, yeah, it works quite well. Okay, so that's it.